Check. Okay, let's start. If you didn't pick up your midterm on Friday, they're in my office. Come by during office hours. You can go through the box with the midterms in them. No real time limit on that. As a matter of fact, I do keep them for a couple of extra quarters. So if you come by 6 months from now, you could probably find all my old papers. I do start to throw them away after they start taking up too much space. So. But certainly not before the end of the quarter. Homework 8 was moved to Wednesday. I'll see if I can get through all that material today. I'm not sure if I will, but we'll just see how far we get. In any case, everything you need to know is in the text. PA5 is extended to tonight, 10 a.m. Started at Friday. One last day, I said. All right, so I don't want to push this any further because it does take the grader time to get it done, and it's got to get done before the end of the quarter. It's really just this week and finals week, and then I got to submit final grades. So if I go any longer, there's not going to be time to do that. So please get something turned in by tomorrow at 10 a.m., okay? If you haven't done so already. I'm not even going to ask how many have completed it or not. It's just got to get done. Turn something in. Now, where did we leave off last time? Are there any questions out there? Go ahead. Final review. I should be putting that up pretty soon, right? Because the final exam itself is when? Final exam is Thursday, March 23. So it's a week from this Thursday. That's the final exam. Okay, well, I'll certainly have it posted by Thursday. Okay. If you don't see it by Wednesday, send me an email, and I may have forgotten about it. Okay, where were we last time? Well, we got through heaps. We know what a heap is. We know how to implement a heap, how to create a heap, a max heap, out of an unordered array. And we know, well, in case I didn't mention it, it is an exercise to go through and rewrite everything in this chapter from the point of view of a min heap. So we could also make a min heap. The heap sort algorithm then, if you just change it to a min heap, would then naturally sort in decreasing order instead of increasing order. Okay, so the question is, how do you create a priority queue out of a max heap? I'm talking about a max priority queue out of a max heap. As an exercise, go through and rewrite all these algorithms to create a min priority queue out of a min heap. Remember now, heap is a data structure. Priority queue is an ADT, right? It's a purely abstract thing. It's really just the states and the interface that allow you to interact with those states. Okay, so here's the heap maximum. The maximum in a max heap is always contained at the root of the almost complete binary tree, which is stored at index 1 in the array. So just return that. That runs in constant time. Heap delete max. So what do? You take the the root, the value at the root, and you swap it with the value at the rightmost leaf. So those are the elements in the array at index 1 and index heap size. Swap those. Decrement heap size. So therefore, I have now excluded what was the maximum from the heap. But I've disturbed the heap property. But I've only disturbed it at one node, and that node is the root node. It still exists, it's still valid, in the left subtree and the right subtree. One of those two is smaller than it used to be because I just deleted something from the heap, but still the max heap property is valid in those two subtrees. And therefore, I can call heapify on the root. I do so, and that reestablishes the heap property throughout the tree, the max heap property. Its runtime is theta log n because of this call to heapify. Okay, heapify we saw runs in time log n. Heap delete max, that wasn't one of the ADT operations, but we could make it an ADT operation. If we were really concerned about the purity of separating operations into access functions versus manipulation procedures, this is a pure manipulation procedure, whereas the one we mentioned before, heap extract max, is kind of a hybrid. It both returns and deletes the element, the maximum element or the element with the maximum key value. Okay, so store the maximum somewhere, delete it, and then return the maximum that you stored. This also runs, I didn't get a chance to write this down, but this also runs in time theta log n because that's constant. 2 has cost theta log n. Okay. Next on the list, heap increase key. So what do we give it? We give it an array, we give it an index I, and we give it a new key to increase it to. Precondition of this is that I is in range. So I has to actually be the index of something in the heap, some node in the tree. That's a precondition. So 1, if k, the new key, is greater than the existing key at index I, then 2, set AI to be the new larger number. Notice this will do nothing in the case that k is equal to or less than AI. And I think I mentioned last time that the book would treat that case as an error condition, but I insist on not treating it as an error condition. It's not really that big a deal, but now what have we done? We've just reached into this tree and we have increased one of the values at one of the nodes. So what's the problem with that? Well, we started with a valid heap, so that node's 2 children were less than or equal to it, and we just increased the value at that node. So that inequality has to remain true. It's even more true now that we increase the parent. So what's the problem? What problem needs fixing now? Where could there possibly be a violation of the max heap property? Obviously not between this node that we changed and its 2 children, because we just increased it. We made it bigger. We made the heap property even more true. Where's the problem now, if at all? The parent. It's parent. So unlike heapify, you remember, we go in and we change something and we possibly made it smaller and thereby causing a potential problem between a node and one of its 2 children. That caused us to have to climb down a line of ancestry to a root, fixing the heap property as we went. That's the way heapify worked. This is the inverse of that. The problem, if it exists, is above the node that you just changed. It is between that node and its parent. So you're going to find yourself climbing up a line of ancestry as far as possible, in worst case, as far as the root itself. So while I is greater than or equal to 2, while I'm not at the root yet, and a parent I is less than AI. This is possible because I just increased AI. It wasn't possible before I did this assignment, but it is possible now. So while there's a violation of the heap property between I and its parent, and I'm not yet at the root, so there is a parent, this guy has a parent, then 4, do what? Swap AI and a parent, parent I. And now what? What have I done? Well, the parent, which is the grandparent of I's 2 children, was greater before than I, which was greater before than the 2 children. So that grandparent is greater than or equal to its 2 children. So we fixed the problem at I by putting the grandparent there. But we just made the grandparent bigger. So now where's the problem, if anywhere? It's between the grandparent and the great-grandparent. That's where. So we need to climb up the tree. How do we climb up the tree? So unlike heapify, this is not recursive. This is purely iterative. 5. So let the local variable I climb up the tree. Set I equal to parent I. So notice we're making I smaller. Right, by climbing up the tree, we just set I to floor I over 2. So I got half its own size. So it just jumped up to its own parent, and now I do the same, I test this same condition again. If I'm not at the root and there's a violation of the heap property between I and its parent, well, that's what was the parent of I and the grandparent of I. We just moved up the tree by setting I equal to parent I. So this is really asking between the parent of I and the grandparent, the parent of the original I and the grandparent of the original I. If that's a violation of the heap property, then we do something about it, and we swap and we climb up the tree again. We keep doing that until either there's no violation of the heap property or there is no parent to have a violation with. That's when I equals 1. Okay. So that's it. What's the runtime? Just think about it for a second. Think about how we reasoned with heapify. Climbing up a line of ancestry. The worst case runtime is the maximum possible length of a line of ancestry. How long is that? Go ahead.
Why can't we just call heapify on the parent of I?
Calling heapify on the parent looks down. Heapify looks down and fixes problems. You see, that would... the problem is, let's see, why can't we just call heapify on the parent? You're saying there's a problem between the parent and one of its 2 children, right? And that's what heapify fixes, right? But heapify has a precondition. What was its precondition? The heap property has to be satisfied at both children. Yeah, that's not right. I mean, what if you go ahead?
Because I feel like if you're doing something like this, it's going to be a constant time operation. But if you call it
They're both log time. This is log time.
I'm talking about in the loop. In the loop
The loop executes log many times
here, but
because it's climbing up a line of ancestry.
if you're swapping the children with his parents, it will cost a constant time. But if you're calling a heapify within the loop, each loop will execute for long n.
But he's suggesting that we eliminate the loop altogether and just call heapify once at the parent.
But if you call heapify once, they won't climb all the way up to the top. They will climb
It's true, it won't climb all the way up to the top, and I'm in the middle of trying to explain to him that that won't work. That a single call to heapify at the parent won't solve the problem. Why not? I mean, what if you increase the key to positive infinity, right? Yeah, heapify will establish the heap property from the parent all the way down. So make the subtree rooted at the parent into a valid heap. But it does nothing to make the whole tree a heap. Right? It works only on the subtree rooted. If you call it on parent I, it fixes the heap property in the subtree rooted at parent I, and that's all it does. So it'll make one swap, and that's all.
What if he called it after the heapify? He called it on the parent like a new.
So what you're really suggesting is kind of a recursive version of this. Okay. Yeah. So then you'd have to check and see if there is a yeah. See, the whole point of in a way, what you shouldn't be calling heapify, because you only know that you already know there's only going to be one swap. So why call heapify? Heapify walks all the way down the tree. It's never going to be necessary to walk all the way down the tree. Heapify is the wrong tool here. Heapify looks down. This needs to look up. It is possible to write a recursive version of this, and I will leave that as an exercise. So I ask again, what is the runtime of this algorithm? Say again, floor log base 2, it is, well, right, let's go back to what I said. I mean, you're giving an answer to a question I asked like 5 minutes ago. The worst case runtime is climbing up a line of ancestry. Therefore, the worst case runtime is the maximum possible length of a line of ancestry. Leaf to root, or root to leaf, whatever you want. That maximum distance is floor log base 2n, correct? I mean, we figured that out. That's the height of a almost complete binary tree on n nodes. So the runtime is therefore, I heard somebody say that, since that's the right answer. So the runtime is theta log n. Okay, that's the runtime. So far, all of our runtimes are log n. That's why, other than get max or the heap, what was it called? Heap maximum. That ran in constant time. Everything else runs in log time. Excellent runtime. Okay, so there's one more. Heap insert. Okay, let me do that. Heap insert A, K. All right, so what does heap insert do? This inserts a new record into the priority queue with key K. That's what it does. But remember, this is all stored in an array of fixed length. So the precondition is that there's room in that array. And the precondition is heap size A is strictly less than length A. there's at least one more slot left in the array to push something into. Okay, 1. So 1, heap size of A is incremented. So increment heap size. Now, so I've got one more index in the array that I can use, and that index is heap size, the new larger value of heap size. So 2, set A bracket heap size A to k, right? No, not k, to negative infinity. Why negative infinity? Well, I know that by sticking negative infinity in at one of the leaves, a new leaf that I've opened up, I will not be violating the max heap property. There is absolutely no way to violate the max heap property by putting in the smallest possible value. That's what negative infinity represents. But that's not the value that I wanted. The value that I wanted was k. So 3, I already wrote the algorithm to do that. Heap increase key. A index heap size A value k. So that algorithm and that loop automatically resets the negative infinity. It was just a temporary value to begin with, to k, and then starts climbing up a line of ancestry until, doing swaps until there's no violation of the heap property, or you could possibly reach the root itself. What's its runtime? Same as heap increase key, log n. Theta log n. Okay, so this is why heaps are thought of as the best way to implement a priority queue. Everything runs in time log n. That's considered an excellent runtime. Now, here's a few exercises. I think some of these are homework problems. Write min or heap min, delete min, and extract min rather, extract min, and decrease key. Oh, while we're at it, rewrite insert. All, so I guess you should put the word heap in front of them, right? I just decided not to. All of these have to be rewritten for a min priority queue implemented as a min heap. In case I didn't state the exercise or write it down, you already have it as an exercise to go rewrite all the, heapify and build heap and all those things from the point of view of a min heap. All it amounts to is change the names of some functions and flip certain inequalities in order to make the min heap property satisfied instead of the max heap property. Okay, why did I include insert? What do you suppose, what's going to be the difference between insert for max heap versus insert for min heap? Just look at that code right there and tell me what one thing is going to change. Yeah? Positive infinity instead of negative infinity. Thank you. Okay. And over here, what's going to change? Swap that inequality, that's all. And change the name of the function. Decrease key instead of increase key. Otherwise, everything stays the same. Okay, so that almost concludes our talk about heaps and priority queues. I want you to notice something, though. Throughout this whole discussion, just one more thing to say. The point of view in all of these cases is that we've taken a simplified view of a record. Remember, a priority queue is a finite set of things that we loosely refer to as records. Think of it as some kind of a record in a database or something. And what's required is that each record have a key field. Well, we've acted as if the key field is all there is, right? That AI is the key stored of the record at node I, right? So that the value is the key, the only thing we care about. Here's our picture. Here's an array A, index 1 through n, say, and the values stored in the array are keys. In other words, there is no satellite data. Here's the general picture. The real picture, if you will, that we're kind of avoiding. By the way, I don't think the book mentions any of this. They don't mention that they're taking a simplified view. So, what's really stored at each index is a record, or more generally a pointer to a record, or some kind of a record object, if you want to think of it in Java. So here's a record, and there's a bunch of satellite data and a key. So, here's another exercise. So rewrite all these algorithms in the general picture. All the PQ, priority queue algorithms. It's very simple to do. For instance, how would this change? Every time you see AI, you replace it by key bracket AI. So key of this, key of this, key of a parent I is less than key of AI. You swap the pointers now, swapping AI and a parent I. Other than that, so whenever something is assigned to or assigned from or compared to that has an A in it, it now becomes put key bracket around that. And that extracts the key. So that's the only thing you do there. Okay, last exercise. I'm just going to give this one verbally. Implement a min priority queue in both C and Java. Okay, you write the project description yourself. You've seen enough of mine. Write a project description and sit down and write the whole thing, and then write a tester for it the way you always do, you know you should do for any priority queue, and see if it works. While you're at it, throw in the heap sort algorithm. Okay. How long should that take you? I don't know, but wait till spring break to do it. You might be too busy to do that. All right, so now we're going to go to chapter 24, which is single source shortest paths problem in a weighted graph. Okay, first of all, what's the definition of a weighted graph? Well, a weighted graph is either a directed or an undirected graph. Is a graph directed or undirected? That means a vertex set and an edge set, together with a weight function. On edges. So I'm defining what I mean by a weight function. It's a function, W, that assigns to each edge in E, either a directed edge or an undirected edge, a real number. Notice I don't say positive real numbers. In general, negative edge weights are allowed and sometimes useful. This could be generalized further, actually, to include complex weights, complex numbers. That might represent something like an impedance in an electrical circuit. Okay, so a weighted graph is a vertex set, which is non-empty, an edge set, directed or undirected, and a weight function on the edges. So let's also define what we mean by the shortest path weight. Notice the actually, let's first define path weight. The weight of a path is simply the sum for all edges in the edge set of the path of weight of that edge. That's all it is. Just add up all the edges along the path, exactly what you'd think. Note the mixing of metaphors. No, we haven't mixed metaphors yet. Okay, so now I'm mixing metaphors. Shortest and lightest. I should make up my mind. Is it lightest path weight or shortest path distance, I guess? I don't know. It's common to mix metaphors like this here. So delta xy is one of two things. It is the minimum of the weight of P such that P is an xy path, if such a path exists, if y reachable from x. And it is infinity otherwise. Okay. Pretty much exactly what it was in the case of BFS, right? Except instead of counting the number of edges along a path, we add up the weights along the path. That's shortest path weight. And a shortest path an xy path P is a shortest path if its weight is minimum. Again, mixing metaphors. If weight of P equals the smallest possible thing that weight of P can be. Okay? That's the shortest path. All right, so SSSP problem. Pretty much exactly what it was before, but using this new definition of shortest path weight. So one is to, given S in the vertex set, determine delta Sx for all x in V. And for those x in V reachable from S, determine a shortest Sx path. So, just stated that way, it's pretty much exactly the statement as before, but we've kind of generalized what we mean by distance. We have two algorithms that solve this problem, mentioned in the book. They use more or less the same infrastructure. In the interest of time, I'm only going to do one of them. One is Dijkstra's algorithm. The other one is Bellman-Ford. Bellman-Ford only works on graphs with all positive weight edges. So this weight function can only assume positive or non-negative, at least, real numbers. Bellman-Ford allows negative edge weights. Now, did I have a homework problem that involved Bellman-Ford? Oh, shoot. Okay, it's actually very short to include it. So I guess I'll try to include it. The thing is, Bellman-Ford isn't nearly as important an algorithm as Dijkstra. I include it just because the infrastructure is the same, and it's kind of easy to see how Bellman-Ford is working. Dijkstra is much harder to see how it works and why it works. But before I do all that, notice that both algorithms actually find shortest walks. I think I mentioned this with respect to BFS. It's not really insisting. The algorithm isn't making, remember, what's the difference between a path and a walk? Paths don't allow you to visit the same vertex more than once or to traverse the same edge more than once. But yet there's nothing in BFS that checked did I visit this vertex before, or did I traverse this edge before? Actually, there is, right? It looks at the color. If you discovered it before, you don't go there. That's how it does it. But in this case, both algorithms actually find minimum weight walks. The point here is that a minimum weight walk is necessarily a minimum weight path. Isn't that true? Because if your path was really a walk, then there's some redundancy in it that could have been eliminated and get something that is better or cheaper or lower weight. Unless you allow negative weight edges. If you have a negative weight cycle, you could go around that negative weight cycle multiple times. In fact, as many times as you want, and there would be no minimum weight walk, and neither algorithm would work. This is the same as a minimum weight path, unless there exists a negative weight cycle reachable from the source. Let me illustrate with an example. And by the way, throughout this chapter, I'm going to assume that all the graphs are directed graphs, just for the sake of definiteness. Everything we say, though, goes through for undirected graphs. Source, destination, and let's X, Y, Z, W, okay? And I'm not going to fill in the rest of the edges, but notice that if I make this edge weight -10, this edge weight 2, and this edge weight 5, then the weight of the cycle XYZX is what? -3. That's a negative weight cycle, and it is reachable from the source. Okay, so I'm trying to get from source to destination. The point here is that there is no minimum weight walk from S to D. So neither algorithm could work in this case, because they both really are finding minimum weight walks. And they're relying on the fact that a minimum weight walk is automatically a minimum weight path. Now, Dijkstra solves the problem by just outlawing negative weight edges altogether, so this can't happen. Bellman-Ford does an interesting thing. It allows negative weight cycles to exist in the graph, but it allows negative weight edges to exist in the graph, and it even allows negative weight cycles to exist in the graph. But the only problem arises if one of those cycles is reachable from the source. So it actually will detect the existence of a negative weight cycle and, sort of tell the user, it gives a return value. So Bellman-Ford will return false if such a situation exists. So you know that whatever else Bellman-Ford has done, it has not solved the single source shortest paths problem in this graph, because it can't be solved. if you get false out of Bellman-Ford. Otherwise, when it returns true, you know that it has solved the single source shortest paths problem. That's how they work. All right, now I have to tell you what vertex attributes we need. We're going to eliminate the colors. We could include them, but we will not. Parent X has the same meaning as it did in BFS. It's the predecessor of X along a minimum weight SX path. Could be nil if there is no such path. And DX is estimate of the shortest path weight, delta SX. That's what DX is. So every vertex has to have these two attributes. In BFS, the distance estimates all started at infinity, and as soon as the vertex was discovered, it was reduced from infinity to its final value, the actual distance from the source to that vertex that we just discovered. In both Dijkstra and Bellman-Ford, it can be reduced multiple times, because what happens is you're not counting edges anymore. So there's a first time you discover DS, or discover a vertex X. And that means you've found a path from the source to that vertex X. But maybe that path isn't the minimum weight path. Probably has the minimum number of edges, but that might not be the minimum weight path. So dx might go down several times before it reaches its final value, which is going to be delta Sx. Okay, but every value that dx assumes is the weight of some Sx path. It stops when it reaches this value, and at that point it is converged because you've actually found a shortest Sx path, or a minimum weight Sx path. Let's see, what else does this have in common with, I'm just going to say very briefly that the predecessor subgraph and the print path function these are defined exactly as they were for BFS. Okay, so I won't write their definitions a second time. Okay, well. So I said there's some common infrastructure. Here are the two algorithms I'm talking about. So both Dijkstra and Bellman-Ford use these two algorithms. Initialize G with respect to a specific source, S. How does that work? Well, all we do is go through a loop for all x in V to set the distance to be infinite, set the parent to be nil, and then once you're done with that, set the distance to S to be 0. And that's the correct value. So let's see. In both cases, whether or not there are negative weight edges in the graph, this is the right value. for the distance from S to S. Is it not? If there are no negative weight edges, certainly you can't do any better than distance 0. And that's the trivial path. Even if there are negative weight edges and there's no negative weight cycle reachable from the source, then you can't do any better than distance 0, and that's the trivial path. Predecessor 0. So everything is set up correctly for a specific source. And now the most interesting algorithm in this infrastructure. Relax. X, Y. It looks like I'm relaxing 2 vertices, but we're really relaxing an edge. Precondition here is that Y is on the adjacency list X. Remember, all these algorithms are stated in terms of the adjacency list representation. Y is on the adjacency list of X. That's the precondition. So what we're relaxing is the edge from X to Y. And as before, this works for directed and undirected, but all the pictures I draw and all the assumptions I'm going to make from now on is that these are directed edges. All right, so what does this mean to relax? If the distance to Y is greater than the distance to X plus the weight of the edge X to Y, well, what does this say? If this says that, see, I've got a current shortest path that I know about from a current path that I know about from S to Y, and its weight is dy. Maybe I can get there better. If I can get there better by first going to X and then traversing the edge X to Y, then that's a better path. So I should update my values of dy, set dy to be this better, smaller value. And 3, set parent of Y to be the predecessor, the new predecessor, right? The last thing I do is traverse the edge from X to Y. So the predecessor of Y is going to be X. So you see, in these algorithms where you have weighted graphs, we could discover a vertex multiple times. Every time we discover it again, we're getting a better and better and better path. So this kind of encompasses the idea of finding a better path than the one we already have. That's what relax is supposed to do. Let me draw a picture. It'll help to imagine it. Here's S. Here is X. Here is Y. Here's an edge from X to Y. Its weight is something given by the weight function. There is a existing shortest or a known path from S to Y whose weight is dy. There is a known path from S to X whose weight is dx. Now, if instead of traveling along this path from S to Y, I travel first from S to X and then traverse this single edge from X to Y, that's a different path. And if that path has a better weight, dx plus weight of xy, that's the weight of this new path. If that's better than the old weight, update dy and parent y. Why is it called relax? I've puzzled about this many times. I think I was talking to a student about it once, and does anybody have any ideas, by the way? Why would it be called relax? Satisfies what? Something to do with the triangle. Yeah, it's kind of a triangle, isn't it? But I'm not sure if everybody knows what the triangle inequality is, right? This plus this is less than or equal to this. Yeah, that's the triangle inequality. Yeah, but that doesn't explain why it's called relax. What's relaxing about it, right? Does anyone feel relaxed hearing about it? If you do, I envy you. Here's why. Somebody suggested it to me. Suppose that these vertices were actually, like nails pounded into a wooden board, and the paths were actually, a stretched rubber band that you tied to S and then you tie it to Y. So if it's really a shorter path, then if you pull that rubber band off this path and stick it on this path around that one, then the tension on the rubber band goes down. So I think that's where they get the word relax from. Okay, that's interesting. I don't know. Well, whatever the reason for calling it relax, that's what we're going to call it. Note a couple of things about relax. Relax changes at most the fields of Y. It doesn't change anything to do with X. And what else? So here's a postcondition to relax. After relax x, y, the inequality dy less than or equal to dx plus weight of xy is necessarily true. Okay, so either this was true and dy is equal to this number, it's equality, or this was false and this therefore was true already to begin with. So this inequality has to be true after relax xy. Yes? Yes, right. What if we then at some later time find a shorter path to x? Then we haven't yet found the shortest path to y. Because maybe, notice that shortens this path. That actually does shorten this path. It's actually, you're asking a subtle question because it depends on the order in which we relax edges. Which edges in the graph get relaxed before which other edges, and how often? Is an edge going to be relaxed more than once? That depends on the algorithm. Dijkstra and Bellman-Ford take very different strategies as to, which edges do we relax and in which order. So the answer to your question depends on what other vertices or what other edges are going to be relaxed. But notice that if we do at some later time find a shorter path from S to X, then the path we've encoded already becomes shorter because we only all we encoded about Y was what its predecessor was. We didn't encode the entire path in that parent field. Make sense? Okay, so all right, so I haven't shown you the algorithms yet, but let me state some lemmas about this infrastructure. Let x be a vertex, and suppose that after initialize GS, has executed some sequence of calls to relax So relax some edges. And I'm not saying which edges. Some sequence of calls to relax results in dx being finite. Then G contains an Sx path of weight that finite value. So this kind of, all this really does is it validates the intuition that we have about this picture, right? Dx, or rather dy is the weight of an existing path. Well, that's only true, or what this says is that's necessarily true if dy is finite. Suppose dx is finite, but dy is not. Well, that means I haven't really found a path from s to y, but I have found a path from y to x. Then I'm going to reset dy from infinity to this plus this, which will be finite, because this is finite. And that's, in a way, that's kind of the induction step. All right, so you may recognize this as a homework problem. Homework problem that's due tomorrow. I would like nothing more than just to do it right now, and I usually do it, even though it's a homework problem. And if you go back to notes from prior offerings of this class, you'll see it in my notes. But see homework solutions. Okay, so homework solutions are going to be out on Wednesday. All right, so here's a hint. Use induction on the number of calls to relax. In other words, the length of the relaxation sequence, starting at n equals 0. Okay. Let's just think about n equals 0, the base case. When n equals 0, relax hasn't been called any times. So initialize gs is the only function or the only algorithm that's been called. So after initialize, the source's distance is 0 and everything else has infinite distance. So let's look at the rest of the hypothesis. Suppose that after initialize, some sequence of calls to relax, in this case an empty sequence of relaxations, results in dx being finite. Well, the only finite d value, if there's been no relaxations and only initializations, the only finite d value is s. So in that case, the base case, x must be s. What are we supposed to verify? That G contains an SS path of weight ds. Well, there is, of course, an SS path of weight 0. What is that path? Okay, too slow, guys. What is the obvious SS path of weight 0? The trivial path, okay? So the base case is nothing more than just say, look, the trivial path gives it to you. And that, again, is because the hypothesis says dx is finite. The only way dx can be finite after no relaxations is if x equals s, the source. And there is indeed such a path. So that's the base case of this induction. All right, it's a pretty straightforward, strong induction. So I suggest you give it a try. Okay, lemma 2. Do we have time? We have probably enough time for limit 2. After initialize, GS, the inequality delta Sx less than or equal to dx for all x in V is true and is maintained over any sequence of calls to relax. Any relaxation sequence maintains that inequality for all x. Certainly it's true at the beginning because delta Sx is 0 and ds is 0. But this will never be violated. Now, this is actually obvious from the previous lemma, if you think about it. Prove. This we will prove in 1 minute. If this is ever violated, if dx is actually strictly less than delta Sx were to become true, after some sequence of relaxations, then, since this is strict inequality, and it's the negation of that inequality, necessarily dx is finite. Dx is finite. So, by lemma 1, G contains an Sx path of weight dx. But that's impossible. How can you have an Sx path whose weight is less than the minimum? This contradicts the definition of delta Sx as the weight of a minimum weight Sx path. Can't get any smaller than the minimum. So this contradiction shows no such relaxation sequence exists. All right, so I have put the proof of lemma 1, which I say is a homework problem. You'll see the solution. You'll see the proof itself. I've put that on final exams before. And I have put the proof of lemma 2 on final exams before. There is one more, lemma 3. I have to give you that next time. And then we'll look very quickly at Bellman-Ford. And then we'll look very quickly at Dijkstra. Just do the best you can on the problems relating to Bellman-Ford and Dijkstra on the homework. I'm not going to delay it any further. Go ahead.